Now the question says that steam at 0.8 megapascals and 250 degrees Celsius and flowing at a rate of 1 kg per second passes into a pipe carrying wet steam at 0.8 MPa and 0.95 dry. Now after adiabatic mixing, the flow rate becomes 2.3 kilogram per second. We have to find the condition of the steam after mixing. The mixture is now expanded in a frictionless nozzle isentropically to a pressure of 0.4 MPa. Find the velocity of the steam leaving the nozzle, and we can neglect the velocity of the steam in the pipeline. So let's make use of this diagram over here. So let us say you have steam entering from this section, that is section 1, and you have steam entering from section 2. Now the steam which is entering from section 1 has a pressure P1 which is equal to 0.8 MPa. It has a temperature T1 which is equal to 250 degrees Celsius. Alright, and the mass flow rate, which is m1 dot, is equal to 1 kg per second. Now if you look at these wet steam which is coming from the section 2, the pressure at this is P2, which is again 0.8 MPa, but it is 95% dry because it is a wet steam. It is only 5% wet. But we don't know the mass flow rate at this section. We know the mass flow rate at section 3 because now after mixing over here, the M3 dot becomes 2.3 kilogram per second. Alright, and then it mixes in the nozzle over here. So this is the nozzle area. And the pressure at section 4, that is the exit of the nozzle, is 0.4 MPa. And we need to find out the velocity at the exit of the nozzle, which is V4. Okay, so let's first of all find out the mass flow rate at section 2. Now if you look at the whole configuration, and if you go by the mass balance, so m1 dot plus m2 dot is equal to m3 dot. Alright, so this will give you the value of m2 dot, which is nothing but m3 dot minus m1 dot, which is 2.3 kg per second minus 1 kg per second, which gives you 1.3 kg per second. So this is the mass flow rate at section 2. So let us say this is 1.3 kilogram per second. Alright. Now we need to find out the you can say condition over here, that is at 3 after mixing. Okay. Now that can be done with the help of the energy balance of these two streams. So when you have to balance the energy which is coming in is m1 dot into h1 plus m2 dot into h2 is equal to m3 dot into h3. So this is the energy balance equation. So first we make use of the, you can say the input, or you can say the total mass input is equal to the total mass that is there, which is leaving the pipe, and you have the total energy input is equal to the energy which is leaving the pipe. Okay, so now let's find out these values. Now state 1, it refers to this condition. State 2, it refers to this condition. Okay, now we can say that at a pressure of 0.8 MPa and a temperature of, you can say, 250 degrees Celsius, the enthalpy is H1, which is from the steam tables, will be around 2950 kilojoule per kg. So this is what you find out from the steam tables. Alright, now let's try and find out the value of H2. Now because it is in the liquid and the vapor mixture region, so H2 will be equal to HF2 plus X2 into HFG2. So this is a very simple thing. So find out the HF value at this pressure, which is 0.8 megapascal, and this dryness fraction. So corresponding to these two things, find out HF2, which will be about 721, okay, 0.11. Now X2 is how much? 0.95 into HFG again from the tables, 2048. So the complete value of H2 would come about to be 2666.71 kilojoule per kg. So this is the value of H2. So now if you put in the values of H1 and H2 over here, that can be easily found out by making use of the stream tables. We can find out H3. So this is pretty much the condition at the, or you can say the condition after the mixing of the two streams. So let's put in these values and find out H3. So that will be equal to 1 into H1, which is 2950, plus 1.3 into H2, which is 2666.71, divided by M3, which is 2.3. So when you do your magic with the help of your scientific calculators, the value of H3 would come about to be 2790 kilojoule per kg. So this is the condition at the, or you can say condition after the mixing. Okay, so this is what you need to find out. Alright. Now the second part of the question is to find out the velocity of the steam which is leaving the nozzle. So let's redraw the nozzle over here. So let us say this is the nozzle. Alright. So this is section 3 and this is section 4. And this is an isentropic and a frictionless expansion that takes place. Now if we neglect the velocity of the steam in the pipe, so you can say V3 is almost equal to 0. Okay. And V4 is equal to a question mark. So if you apply the steady flow energy equation for a nozzle, you will have H3 is equal to H4 plus V4 square by 2. So this is what you get. Okay, so in this I know the value for H3, but I don't know the value for H4. So this is a task that we have to find out. Now as the steam expands isentropically in the nozzle to a pressure of 0.4 megapascals. Okay, so let's find out the value of H4 from the steam tables. So one thing we know that because it's an isentropic expansion, okay, it's an isentropic expansion. So let us say this is S3 and this is S4. So both of these entropies would be equal. Okay, so you can find out the value of entropy at state 3. Okay, now state 3, you know the value of, you can say enthalpy over here. So the enthalpy at state 3 is 2790. So if you interpolate a bit, the pressure at state 3 is also 0.8 megapascal. So the pressure is not decreasing or increasing. Okay. So at this pressure and at this enthalpy, you can pretty much see that what would be the temperature. So by interpolation and by a little bit of approximation, you can say that the temperature would be somewhere about 179 degrees Celsius from the steam table. So this is what you will get. Alright, so you can say that corresponding to 179 degrees Celsius and a pressure of you can say 0.4, I can find out the value for S3. So S3 is equal to, from the tables, around 6.7, or to be exact 6.7087. Okay, now S4, because 4 would be somewhere in the region of the mixture, so you will have S3 is equal to S4, which is SF4 plus X4 into SFG4. Now from this I can find out the value of SF4 and SFG4 corresponding to this pressure. Okay, so you can find out these values from the steam table, and this equation would give you the value for X4, that is the quality of the steam at state 4, that is at the exit of the nozzle. So that would be somewhere about 96%, 0.964. Alright, now you can easily find out H4, because H4 would be HF4 plus HFG4. G4. So again, corresponding to 0.4 megapascals, you can put in these values. So you make sure you are using a steam table for all of this. So this would be around 2660 kilojoule per kg. So this is how you can find out H4. So now if you put it in this steady flow energy equation, I can easily find out the value for the velocity at the exit. So velocity at 4 would be equal to twice into H3 minus H4 into under root of this. So this would be somewhere about 509.9 meter per second. So this is how you solve this question. Now a very key point that you need to understand in this question is that when you make use of this particular state to do the calculation for the nozzle part, you need to have the temperature also. Because we just had the enthalpy at state 3, we also need the temperature. So temperature, how you have to find out? I am repeating again. I did this when I was doing the question. Now at state 3, this is the enthalpy and this is the pressure. So corresponding to this pressure and then this enthalpy, you have to find out approximately that it is corresponding to which temperature. So as per my steam table, it is coming about to be 179 degrees Celsius, which is still in the superheated range of the steam. So this means that you might have 181, 182, 178, so it is all the same. So it is just an approximated value. Alright, so your velocity should lie between 509 to 511 meter per second. That's the amount of error you can is acceptable in this kind of a question. So the temperature was a required value, which is not exactly calculated, but we can only find out by making use of some approximation or just by looking at the steam table that yes, this is lying in this region, so this must be the temperature for which it corresponds to. Now when you look at this this nozzle, you need to find out H4. Now first of all, because you are dropping down from a superheated state, you will be coming down into the wet region, so you need to find out X4. So that's why we make use of this entropy equivalence. Alright, so this is how you have to proceed and look at this question. I hope this was a question that you understood. Now let's move on to the next topic.